Hello everyone, welcome to eSpace. This is a new lecture on sequence circuit, part 4. I am Chandra Chandran, MTech graduate from IIC Bangalore. Now working as senior engineer at Keltron. In this lecture, we will be looking on introduction to asynchronous sequential circuits, enhanced procedure of asynchronous sequential circuit, race condition and stability considerations, circuit with latches, and Debounce circuit. So this is a new topic, asynchronous sequence circuit. A sequence circuit is specified by a time sequence of input, outputs, and internal states. And earlier we have studied synchronous sequence circuit, where the change of internal states occurs in response to clock pulses. But this time there is no clock pulses. In asynchronous sequence circuit, the change of internal states occurs when there is a change in input variables. So there's a change in input variable, it changes and finally it reaches a stable state. That's a asynchronous sequence circuit. The memory elements in synchronous sequence circuits are called flip-flops. The memory elements in asynchronous sequence circuit are either unclocked flip-flops or time delay elements. We'll be looking at the block diagram. We will understand that when you will see the block diagram. The memory capability of a time delay device is due to finite time it takes a signal to propagate through digital gates. So this change happens with according to the propagation delay of the digital gates used in the asynchronous sequence circuit. So an asynchronous sequence circuit quite often resembles a combinatorial circuit with feedback. So it is actually a combinatorial circuit with a delay feedback, with a feedback with delay. So the input changes, the states varies according to the input variables. The design of asynchronous sequence circuit is more difficult than that of synchronous circuit because of the timing problems involved in the feedback path. The time delay introduced in the feedback path will be very small. It will be usually in the nanosecond regions. So the speed of the circuit will be very high. So asynchronous sequence circuit are usually in applications where speed of operation is important, especially in those cases where the digital system must respond quickly without having to wait for a clock pulse. So digital designers often produce a mixed system where some part of the synchronous circuit has the characteristics of a asynchronous circuit. So we will be using a mixed system consisting of synchronous and asynchronous parts. So according to the timing required for the circuit. So the figure in the next slide shows a block diagram of an asynchronous sequence circuit. Let us see that. So this is the block diagram of the asynchronous sequence circuit. See, these are the n input variables similar to in synchronous circuit, and this will be output variables. But here you see there's a difference from synchronous sequence circuit, where there will be a feedback taken from output, that is a state, to the input state. That is, there will be secondary variables present. This is the present state and this is next state, and there will be a delay associated with the feedback. So when this y changes, it goes to the propagation delay. It goes to the propagation delay of the combinatorial circuit, and after that only there will be a change. And here with the delay, after that only there will be a change in the present state of the variables. So according to the block diagram, there are n input variables, m output variables, and k internal states. The delay elements can be visualized as providing short-term memory for the sequence circuit. That's the changes in the variables will be happening according to the delay. In a gate type circuit, the propagation delay that exists in the common circuit path from input to output provides sufficient delay along the feedback loop. The present and next state variables in asynchronous sequence circuit are called as secondary variables and excitation variables respectively. So the change in present and next state happens according to the delay in the feedback loop. When an input variable changes in value, the y secondary variables do not change instantaneously. That's the thing here. When the input variable changes, the secondary variable changes after a certain delay. So this delay is the feature of the asynchronous sequence circuit. So when an input variable changes, after a delay it changes and then it's come to the stable state. So it takes a certain amount of time for the signal to propagate from input terminals through the comparator circuit to the Y excitation where new values are generated for the next state. So when the capital Y changes after a certain delay only, the new present state will be available for the secondary variables. So the small y's and capital Y's are same in the steady state, but it different during transition. At the transition time, these two values will be different, but when it reaches the stable state, these two values will be equal. So it is important to realize that a transition from one stable state to another state occurs only in response to a change in an input variable. So according to change only in single input variable only, the transition happens from one stable state to another stable state. Because of the delays in the bias and gate circuit, it is impossible to have two or more of changes in input variables at the exactly same time. So there will be only one or two changes in input variables at the exactly same time. So only one input variable can change at any one time, and the time between two input changes must be longer than it takes a circuit to reach a stable state. So suppose there is a time to reach a stable state, though, so the input variable must change longer than this time. That is the times to reach a stable state. This type of operation is defined as fundamental mode. It assumes that the input signals change one at a time and only when the circuit is in a stable condition. So when the circuit is in a stable condition, only one or two only input signals will be changed at a time. So let us do some analysis for a circuit. For example circuit, consider this circuit. This is the input variable x, and this is the output state. The next state y1, y2. At the output, it is a capital Y1 and capital Y2. At the input side, it is after the feedback, it is small y1 and small y2. This is the present state, and we have written the equation for y1 and y2 as a function of x and y1 y2. So this is the equations here. We are that is our analysis, and we have written the equation for the Boolean expression for that. And this is the map for y1, k map for y1, xy1 plus x bar y2 according to the circuit. So these are the output values, and this is the map for y2. These are the output values according to the values of x, y1 and y2, and this is a map for y2. And this is a transition table. It's a new thing, and that is transition table is defined for a asynchronous circuit. And these are the present state y1, y2, and this is the input x. And according to the change in input, there is a change in output. The output, that is the next state, that is the capital Y1, capital Y2, and we have merged these Y1 and Y2 to get this transition table. And these circled ones are stable state. At this state, it is stable. See, this is the present state of y1, y2, that is 0, 0. And when x is equal to 0, this is the next state of the circuit, that is the capital Y1, capital Y2. This is written here 0, 0. And this time, and when x is equal to 1, when y1, y2 is equal to 0, 1, then the next state is 0, 1. That's a stable state. And there are 4 stable state, and these are the transition state. The uncircled ones are the transition state. So this is a transition table defined for the circuit. And this is a state table. The present state, when x is equal to 0, this goes to 0, 0. When x is equal to 1, present next goes to 0, 1. And these are all the stable state written as in the state table. So next we define a flow table. A flow table is similar to transition table, except that the internal states are symbolized with letters than symbols. And so here there is no 0, 0, 0, 1 like that. And instead of that, we have defined a letter for the stable state. That is, here it is for a state we have defined a letter, that is for 0, 0 it is a. We have written a here, and 0, 1 we have written a b. Like this it goes on. So these are the this is a flow table for the present circuit, 4 states with one input. This is a flow table. So and that so that is over. Now let us see the flow table of an example circuit. Here we define a flow table. So from here we have to generate a circuit. So this is the flow table, and this comma after comma it is there is a output y that is defined here in a flow table. That is, here we have defined the flow table, and from this flow table we have to uh, generate a circuit. So this is a flow table. So now let us, we have to make a transition table for the circuit. So this is a transition table. So instead of ABCD we have written 0 and 1 here. So from the transition table we have generated y, equation for y, that is x1 x2 bar. So this is x1 x2 bar plus x1 y. So that's it. We have derived the Boolean expression for y here, and this is the equation for output, that is output is z here. So that is x1 x2 y. So that is this variable. So here this is x1 x2 y, and here in earlier in for y we have generated from here, we have merged these two one according to the k-map rule. So that is x1 x2 bar plus x1 y, and this is a required circuit. So from the according to the Boolean expression we have generated the circuit. So this is a required circuit. So let us now see some properties of the asynchronous circuit, that is race condition and cycle. A race condition is said to exist in an asynchronous circuit when two or more binary state variables change value in response to a change in an input variable. So suppose there is an input variable and there are some states in the asynchronous circuit. So when some input variable changes, so according to that some state is changed, then it is called the race condition. And there are non-critical race and critical race. So if the final stable state that the circuit reaches does not depend upon the order in which the state variable change. Suppose the variable changes but the stable state does not depend upon the variable change, then it is called a non-critical race. That is, there will be a stable state for every changes in the circuit, then it is called the non-critical race. And the critical race, if it is possible to end up with two or more different stable states. So here in non-critical state there is only one stable state, but in a critical race if there are two or more different stable states for the state variable change, then it is called the critical race. So for proper operation critical races must be avoided, but non-criticals may be present in the circuit. The races can be avoided by directing the circuit through intermediate unstable state. So there is some stable state chain, and between that if we insert some intermediate unstable state, then the circuit is said to have a cycle. So when a circuit goes through a unique sequence of unstable state, then it is said to have a cycle. So that is called a cycle. So this is an example for non-critical race. So this is a transition table of a circuit, some circuit, and here you see there are stable state 0, 0 and 1, 1, and there are some intermediate changes also, but the final stable state is the same here. So that it is called, it is a non-critical race. Here again in this circuit also, in this transition table there is state transitions, but the final stable state is the same. And this is an example for critical races. Here you can see there are different stable state according to the input changes. So it is called critical races. Again you can see there are different stable states for this transition table. So it is called critical races. And this should be avoided because that is a malfunction of the circuit. And here again there is one stable state, but we are inserted some intermediate states, intermediate states. So this is called a cycle. Again this is called a cycle, and here it is unstable. This circuit is unstable because it goes in a loop like this 0 1 1 1 1 0. It goes through a loop, so that is called unstable. So let us have some stability consideration for the asynchronous circuit. So because of the feedback access in the asynchronous circuit, care must be taken to ensure that the circuit does not become unstable. So earlier we have seen the unstable circuit, and unstable condition will cause it will cause the circuit to oscillate, and we have to take measures to not to not the circuit to oscillate. So but that also might be required for certain applications. Suppose for certain application this oscillation must be required. For that we have to design properly and mm, make the circuit to oscillate for the certain application. So consider this circuit. For example, that's a NAND gate here and the AND gate here. There are two input variables, and this is the present state and next state with the feedback. So this is the small y, and this is the capital Y here as usual. This is a logic diagram here. So let us analyze. So this is the excitation function, that is x1 y is equal to x12 plus x2 y bar. So here you can see this is a transition table for the circuit. So the circled entries are the stable ones and uncircled entries are unstable. So suppose when x1 x2 is fixed at 1 1, the values and y are not the same. You can see the according to transition table you can see. So if y is equal to 0 and capital Y is equal to 1, which causes a transition to the second row with y is equal to small y is equal to 1 and capital Y is equal to 0. So that means the circuit oscillates again. So again you can see that x1 equal to 1, x2 equal to 1 and small y equal to 1. The output of NAND gate equal to 0 and output of the NAND gate equal to 0 and AND gate output equal to 0. That is capital Y is equal to 0 and so y is not equal to small y is not equal to capital Y. So this value changes after a certain delay. So now if y is equal to 0 and AND gate output equal to 1, and now the AND gate output equal to 1. So that is capital Y is equal to 1, and so again y is not equal to y. So so this happens with according to a certain delay of the gate involved in the circuit. So assume each gate having a delay of 5 nanosecond, we will find capital Y will be 0 for 10 nanosecond and 1 for 10 nanosecond. So that will result in a square wave of period 20 nanosecond. So that means that the circuit produces a square waveform when x1 x2 equal to both are equal to 1, and now the frequency equal to 50 megahertz. So suppose we want a circuit to make it to oscillate, we can design like this, and if it is not required, then that is a unstable circuit. So now let us look the circuit with latches. The latches is a asynchronous circuit, and there is no clock involved for the transition in the output. So consider this NOR latch. This we have already seen. When S is equal to 1, that is a set condition, and R is equal to 1, that is a reset condition, and when both S and R equal to 1, that is a forbidden state. So we will be doing an analysis here for the NOR latch. So this is a circuit showing feedback. We have you can do in both ways, but this is one of the ways, and I have read on this circuit according to the theory of asynchronous circuit, and this is a transition table here is SR. So these are the stable states. In the circled one, that is a stable state. These are the transition state. So this is a Boolean function of the circuit showing in feedback, that is SR bar plus R bar Y. So when we see the transition table, we note that going from SR11 to 00, that is at 11 there is a forbidden condition. So if S go to 0 first, the output remains as 0, but if R goes to 0 first, then the output goes to 1. That is the situation here. So we have to mask this forbidden condition, that is SR equal to 1 1. So for normal event, we must take sure that S and R is not 1 simultaneously, and which can be expressed by the Boolean function SR equal to 0, which states that ANDing of S and R must always be 0. So that is, suppose this is a sum of product expression. So suppose if we OR a 0 with this, that makes no change. So we are ORing this Boolean expression SR bar with SR. We are ORing with this equation, that is SR bar plus SR, that makes S. So that is the equation here. So Y is equal to S plus R bar Y when SR equal to 0. So that is equation for the latch without forbidden condition. So consider now this NAND latch. So again, this is a same condition. That is when S is equal to 0, that is set. When R is equal to 0, then that is reset. But when both are 0, that is a forbidden condition. So the difference with NOR latch is that we have to complement all the S and R values. Then we will get the expression for NAND latch. So this is a circuit showing feedback here, and this is a transition table. These circled ones are the stable states. So here, so when it is 0 0, there is a forbidden state here, that is both are 1. So we have to solve that. So this is a Boolean function. This we have expanded here, we have converted here this equation S bar plus RY. So here when we see the transition table, we note that going from SR, that is 0 0 to SR equal to 1, it produces a unpredictable result. When if S goes to 0 1 first, the output remains to 0, as well remains as 0, but if R goes to 1 first, the output goes to 1. So for normal operation, we must make sure that S and R is not 0 simultaneously, which can be expressed by the Boolean function S bar R bar equal to 0. So that is a 0 condition here. So which states that ANDing of S and R must always be 0. So that is, so ANDing of S and R, S bar and R bar must always be 0. So we can OR the Boolean expression SR bar with S bar R bar, that is we can OR like this, we can OR here because this value is 0. So but you will get the expression shows that it is S bar only. So the equation for the circuit is Y is equal to S bar plus RY when S bar R bar equal to 0. So this is the equation for the NAND latch without forbidden condition. So let us now see how to implement a latch without forbidden condition. So this is Y and Y. This is the present state and this is the next state. This is the SNR input. So we will write a excitation table for the NOR latch. So when value changes from 0 to 0, it is 0x. 0 to 1, it is 1 0. So that is a set condition. And 1 to 0, it is a reset condition, that is 0 1, and 1 to 1 it is x0. So we will draw the transition table for the NOR latch. So for any latch it will be, this is a transition table. So here there is no forbidden condition, this is a transition table here. So this is a state table to generate the value of x s here. So this is x1, so we are writing s as a function of s x1 x2 y, and according to the transition from y to this capital Y, small y to y, we will write the value for s. So here when it is 0 to 0, we have seen earlier in the excitation table it is 0, and 1 to 0, here the excitation table, according to excitation table, this s is equal to 0. 0 to 0 it is 0, 1 to 0 it is 0, 0 to 1 it is 1, and this value will be get from the transition table, where after when x1 and x2 and y equal to 0, the output value will be 0, that is y will be the next state value will be 0. And from this transition, according to a transition, we will write the value for S. So this is the values for S, and this value we will be writing in a K map, and we will be generating the equation. And this is x1 x2 bar. S, the value of S is x1 x2 bar. And similarly we will be finding for R, that is R is equal to x1 bar. See here, this x1 bar here. So this is the required circuit. We are converting the NOR latch to where the forbidden state is not involved. So next is NAND latch. Similarly, the excitation table is different for NAND latch, and when y is y to y to the small y to y 0 to 0, then we have 1x. From 0 to 1 it is 0 1, 1 to 0 it is 1 0, and 1 to 1 it is x1. This is a transition table that is the same, and this is the equation, the state table for generating the value of S. Again we have written the same as a NOR latch here. This is a, from the excitation table we will get these values, and this will be writing according to the excitation table the value of S, and we will be writing into the K map here, and to generate the value of to find out the value of S, that is here we are obtaining this value, that is S is equal to x1 x2 bar the whole bar. See here, if we deduce this expression, we will be getting like this. And again, this is the value of R. The same procedure happens here. This is the map for R. See, you can find here this x1, the value is x1, and this is the required circuit where the forbidden condition is avoided. This is a NAND latch here. So next topic is Debounce circuit. So usually to enter information into a data system, we will be using keyboard or such key or a mechanical switch, and one position provides logic 1 and other logic 0. But the common characteristics of the mechanical switch is that when we press the switch, the switch contact vibrates or bounces several times before coming to the final result. That is, the key vibrates vibrates several times, but that is there will be some oscillations before the switch come to a final stable state. So there will be some changes from 1 to 0, that there will be some oscillations before the switch comes to a final stable state, and this takes several milliseconds to die out and may oscillate between 1 and 0. So a Debounce circuit is one that removes the series of pulses that result from a contact bounce and produce a single smooth transition of the binary signal from 0 to 1. So without the Debounce circuit, the value to the input, the information to the data system will be in an error. So the Debounce circuit is one that it removes the series of pulses, that is, it removes the oscillations and give a steady 0 to 1 or 1 to 0 transition. So this is a Debounce circuit for a SPDT switch. That's here you can see this is a SPDT single pole double throw switch, and this is the ground. This is ground here. So suppose it is at position 1, that is a position A. So when we press A, it bounces from B to A. So there will be some motion, but when just you can see here, when this is at this position, this switch position is at A, that is 0, that is it is a set condition here. So Q turns to 1, and when it is not remaining in position A, it will be 1 1 to the NAND gate or the NAND latch. So there will be that will be the same state. So there will be a single transition from 0 to 1. So here you can see when the switch is turned from A to B, the Q goes low, and when it turns to B to A, again does not bounce here, but it gives a single value at the circuit, at the output of the circuit. So let us now see Debounce circuit for SPST switch. This is single pole, single throw. There is only one side. So when this is when we press the switch, it first makes a contact at the S here for a small time. So that makes the Q to 1, and then it oscillates here, but it makes no different at the output of S, different of the output of the latch, because when the switch does not make contact here, that is it is at logic 1 1, that is the latch remains in the previous state, so there will be no oscillations here, and we will have a only one single transition from 0 to 1. So that's it for this part. We'll be taking more topics from asynchronous sequence circuit in the next slide, next lecture. So please like and share the video, subscribe the channel, and thank you. If you have any comments and doubts, you can mail me to chanch484@gmail.com or put at the comment section of the YouTube. So thank you everyone.